All right, I want to talk to you about how perspective really works. I get so frustrated listening to flat earthers use the word perspective and how they use it so terribly incorrectly. I hear all kinds of uses of perspective. Sometimes they're trying to use it, yeah, realistically or accurately, and then they use it mistakenly. Other times I've heard people just have no interest in how it's supposed to be used, but just um, try to use it in sort of just drop it into their sentences in a way that doesn't really make sense or really isn't what visual perspective is about. Sometimes people slide back and forth where they're trying to talk about perspective and then talk about like it's their point of view, which is a slightly different thing. But I want to talk about visual perspective, how things appear to get smaller as they're further away and so forth, that kind of perspective. So here are just a couple examples from Flat Earth people talking about it. Here you can see this person is trying to show that the perspective causes things to appear lower or shorter as they get further away, and so that causes the sun to get uh, appear smaller. This person, I like this. I'll play a little bit of this one.
But of course, in reality, we do see the surface and the sky appear to meet at eye level.
Now, hold on. I just want to pause about this for a second because things appear to meet at eye level, and they use all these photographs to prove that. Most of the time, people just point their camera at the horizon because that's what's interesting. And so, using a photograph to prove that everything always meets at eye level is kind of ridiculous because it just depends on where people point their camera. But that's a separate issue.
At the vanishing line of the observer's point of view or perspective. And we know from personal experience and observations throughout our lives that we see the same phenomenon when we are looking at parallel lines going off into the distance, such as train tracks which appear to converge at the vanishing line of the observer's perspective or point of view. We also see the same thing when we are looking at lampposts going off into the distance, and we see this with looking down long corridors that appear to converge.
Okay, so anyway, somehow all that is supposed to go on to explain why the Earth is flat, and uh, or how the sunset could work on a flat Earth, and I just don't see it. And we're going to talk about why. Is that they're just flat wrong. Okay, so the most important thing to understand is how the eye works, right? So and there's, it's obviously a very complicated organ, but here's the basic thing that is important for us. So as the light comes in off the top of the ice cream cone, it travels down through the lens, gets bent, and ends up at the bottom. Now, normally light travels in a straight line, except when it's refracted here, so it's being refracted through the lens, ends up at the bottom. And then here, light comes from the bottom, travels up to the top of the lens, it's refracted, but still ends up at the top of the image. Like it doesn't completely flip it around, it still brings that light to the top of the image. Light from here ends up at the bottom of the image. Okay, so here's another illustration of the same idea, a picture of a tree, and the light gets the image is turned upside down, but then our brain flips it around again. Now it's a little bit like what happens in a pinhole camera. Now normally there'd be in our eye there's a lens right here. A camera would have a lens like here, but this is what happens in it's a little more simplified, but it works sort of the same way. Light comes in from the top, ends up at the bottom. Light comes in from the bottom, ends up at the top. Light always travels in a straight line. And that's really important to understand how perspective works. So, and what we're going to look at here is if we stretch the image out here, move the tree further away, it makes this angle smaller, makes that angle smaller, and then we end up with a smaller image. So the light from here goes down, ends up at the bottom, here ends up at the top. But because this angle is smaller, caused by the tree being further away, it makes the image of the tree inside their eye or inside the camera appear smaller. So I'm going to give us some examples, a more detailed look at what's going on here. So I made this kind of silly looking little eyeball, and I simplified the lens. I'm leaving out the refraction part of it. I know that that helps make it the focus and stuff, but I'm going to simplify it because that's not really what makes the big difference in perspective. So the light comes from again from the head and comes down from the top down to the bottom. The light from the foot goes from the bottom up to the top. And then we end up in an inverted image. Because the image is fairly large, the image, it's fairly large and fairly close, the image ends up being large inside the eye. So if I move this person further away, you can see that they're the same size person. I just move the person further away. The light does the same trick, but it ends up creating a smaller image. You can see this angle gets squeezed down a little bit, and so that squeezes this angle, and then that makes the image smaller. And then move the person still further away, and the light from the top goes to the bottom. But you see what happens is this image angle gets really tight, and the result of that is a very small image over here. So just moving the person further away causes the angle to squeeze down like that. Okay? That's the most important thing that people talk about with perspectives, is that things appear smaller when they're further away. Okay. The other thing that's important with this is, I mentioned the angle there a little bit. It's important to think about the angular size. Like how much, like if you imagine looking around, you've got a big field of view that's like, a big wide sort of a semicircle out here that you're looking at. And the angular size is about how much of that arc does the picture or object you're looking at take up. So a very small object up close can still take up a fair amount of your angular size, but a large object far away can also take up about the same amount of angular size. And filmmakers and photographers love to have fun with this kind of thing because you can do a trick called forced perspective. I know the Lord of the Rings movies used forced perspective a lot to make actors who are all about the same size look, some of them look shorter than others. So that's a lot of fun. But it's all about manipulating and trying to create the right angular size. So this is really important also to understanding perspective. So let's look a little further at how that works. Angular size is actually a geometric phenomenon. You can calculate angular size by looking at a couple of things. One is how far away is the object. So we're making a line here to indicate the distance to the object. And then you can look at the size of the object. How large is it? And it doesn't matter how far away it is or how, you can always calculate the angular size. So the easy way to do that, though, is to take the distance and the size of the object and convert it into a triangle. So here I've made a right triangle, so we can employ trigonometry. You got a right angle here, which is the width across the eye. It doesn't matter if it's the width or the height. This trick works the same for the width or the height of the object. And so the angular size is, remember from trigonometry, is the opposite side of the triangle divided by the adjacent side of the angle will give you the tangent of that angle. So I put the equation here, tangent of half our angular size, because if I want to make a right triangle, I've got to use half the angle. So half the size of the object, half the size is over here, and the distance to the object is the bottom part of our triangle here, the base, and then the tangent of that will give us the angle, or the inverse tangent of that will give us the angle. Okay, now it's simpler if you want to get the whole angle. Just don't use half the size, use the whole size, and it'll make your fraction twice as big, and then that'll make your angle come out twice as big, and that's what you want, right? That'll give us the angular size, so that's what we're going to do here. But a little bit more about that before we go on, because I made up I made this purple rectangle here to help you see that all these bars are the same size. So, and then the lines from each tip of the bar are go off are color coded, so it's easier for you to see. So this line, right, the red comes from the red bar, the purple comes from the purple bar, and so on. Now, I didn't include the lines from the last one because when objects get to be too far away, the angle gets to be too small, and you can't see that your eye can't resolve it. You can't make any sense of it because that angle becomes so tiny that the object just gets too small in your eye and disappears. So that's what some people call the vanishing point. However, there's no such thing as the one vanishing point. There are lots of different vanishing points. Every object has its own individual vanishing point. If something is really small and you move it very far away, you will end up with a picture, or the object will disappear. So if you take a photograph of a field or something, there's probably in that picture a bee or a fly or something, mosquito flying around, and you can't see it in the picture, or your eye couldn't see it because it was too far away and too small. But also at the same time, so you can have like a vanishing point, like let's see, here's this hallway, or earlier he was showing the railroad tracks, like this. So here's the vanishing point of the railroad tracks. But notice we can see clouds that are further away because they're bigger, right? So the vanishing point there's no one vanishing point. It's about the size of the object compared to how far away the object is. The other thing that's important about this is that when you are looking at an object and it's a bunch of same size objects that are further away, you gradually have to lower your eye in order to look at the top of each successive object. So here, having to look up quite a bit to see this point, and then look down a little further to see that one, and down a little further to see that one. This is why lampposts appear to get shorter as you go further away. It's also why train tracks get narrower, right? The same thing happens like this thing, right? The same phenomenon. These bars are kind of like the bars in my picture. They gradually we're gradually having to move our eye more and more toward the center to see the object. It does not mean that the objects are getting lower at all. It just means that we have to bend our eye or angle our eye in a different way at a lower and lower or narrower and narrower range in order to see those things. So that's another important thing about perspective, right? Why this is, they get smaller as they get farther away. This is why. Okay, so what I want to do here is try to help you see how perspective would affect the sun. So I created a little setup here. I put my eyeball. You can see this little white circle is supposed to be the eyeball. Down in the corner, we've got flat Earth on the ground level, and we'll put the sun right up over our flat Earth person, right up over our eyeball observer on the flat Earth, and we'll put the sun at 3,000 miles. Now, some people will say, well, it's not 3,000 miles. I've calculated it to be 3,612 miles or whatever. They've got all these different, people have different things. So you can play around with the numbers if you want. I'm just doing that to keep the math simple. You're welcome to substitute another number and try this yourself. Okay, everybody agrees at noon the sun is at 90-degree angle from the horizon. We're assuming like at noon on the equinox over the equator, so to make it really simple. And then the size of the sun in this drawing is not to scale. The sun is an angular size of about 0.5 degrees. To get angular size of 0.5 degrees at 3,000 miles, you have to make the sun about 27 miles across. I've heard numbers, maybe it's 32 miles across. That would just require you make the sun a little further away than 3,000 miles. I'm just use 27 miles because that's what gives an angular size of 0.5 degrees at 3,000 miles. And again, if you want to play with some slightly different numbers, you're welcome to do that. Okay, so here's an illustration of what that would supposedly look like. We've got the Earth, this part of it illuminated by the sun. And here's the sun over the equator at noon. And so that's basically what we're talking about. So that's our starting point. Okay, so then I have the sun move off across the ground 3,000 miles. So this distance along the bottom here is 3,000 miles. And we're still 3,000 miles up. We can see the angular size is changing a little bit. It's hard to notice yet, but we'll follow along here. So how do we figure out how far is it to the sun? To calculate the angular size of the sun, we need to know how long this distance is. So we can think of this like a right triangle. Here we've got 3,000 miles this way, and we've got 3,000 miles that way. Makes a right triangle, and if we use the right triangle, we can use the Pythagorean theorem. So not too fancy. You should have learned this in secondary education. So 3,000 squared plus 3,000 squared, and take the square root of that because it's about 4,200 miles. So the sun is 4,200 miles away, and that gives us an angular size of about 0.37 degrees. So the sun is already shrinking a little bit, although maybe that you wouldn't notice yet. And also, if we put up a triangle here to try to figure out what angle would this be down here, it would be about a 45-degree angle with the sun. To put up a protractor and you can see it, it's a 45-degree angle, right? So the math, the trigonometry, gives us a confirmed measurement. All right, so let's try this again. We're doing the same. I'm not going to walk through the whole math of every single step here. You can, it's all based on the math from that previous slide. Sun distance 6,700 miles, angular size 23 degrees. This is what happens when I move this 6,000 miles away, still keeping 3,000 miles high. You can see makes a 26.5 degree angle. So this I calculated just with the math. That 26.5 degrees is only calculated with the math. Then I pop in the protractor, and just to check it, I was worried, like maybe I didn't do it right. What if there's something wrong with my math? So I went back and put the protractor to it and found that it was right on. So what I want to think about is what happens at sunset. Because here's our same point, and if we rotate this, have the sun go around along here, how far away will the sun be now? So it's 6,250 miles from the North Pole to the equator, and would also be true in this direction. So we can use the Pythagorean theorem to figure out how long would that be. And that's about 8,800 miles. Okay, so I included a 9,000 mile distance sun just because I'm jumping by 3,000 miles, and it's right 8839 is pretty close to 9,000. So try to figure out what would the sun look like when it's supposedly setting, right? Because here, when the sun is right there, the sun is got to be this person is having sunset. The sun is going down for that person. So that's why we chose this distance. So 9,000 miles makes an 18-degree angle between the ground and the sun. Here's an example of what this would look like. So this is a real photograph of a sunset. That sun is part of the original photograph, but our sun would be at an 18-degree angle. There's the protractor to show you the measurement. And then, but it would be up something like that. And then, but that's too big, right? We've calculated over here, right? We've got an angular size of 0.16 degrees because the sun is 9,500 miles away. So it would actually look about a third the size of our original sun. The sun doesn't look like that. Well, I've never seen a sunset that looks like that. Because like this is 9,000 miles. This is supposed to be when the sun is disappearing, right? The sun is moved off. That part of the earth is now going to be lit I mean, another part of the Earth is going to be lit. My part is going dark. I've never seen the sun disappear when it looks like that. I mean, yeah, so I don't know what that's supposed to be. Okay, but we're still not at the horizon. I mean, look at that, right? We're still not at the horizon. The sun is still way up in the air. We need to get the sun horizon, so we're going to use perspective to try to bring the sun down to the horizon. Okay, so let's go a little further. 12,000 miles along the ground makes a 14-degree angle between the ground and the sun. Sun distance is 12,400 miles. Angular size 0.12 degrees. It's about a quarter of the size of the original sun. We can put our protractor on there if you want to confirm the measurement. 14 degrees. And 15,000 miles along the ground makes an 11.3 degree angle. Bring our protractor in to confirm that. Angular size is about 0.1 degrees. So now we're down to a fifth the size of the sun, but we're still not at the horizon. We're 11.3 degrees above the horizon. So I'm run out of space on my slide because I made everything proportional, right? This side over here, the height of the sun, is 5 times as long as this. Okay, so that's how I get the measure. This angle, this is what it really would look like. Right? That's why I put the protractor up there. I want you to see that you really do get this angle. So we have to keep going to get it down to the horizon. So we try 18,000 miles. That only gets us to 9.5, 21, 8.1. Right? You see it keeps going. 24, 27, 30. And we only made it even 30,000 miles, right? Twice as far as in this illustration. We only make it down to 5.7 degrees. That's not enough. That's above the horizon. So I tried it off 100,000 miles. And there we get down to the horizon, right? Or very, very nearly on the horizon. Kind of like in that picture I just showed you. But look what happens with the angular size. 0.015 degrees. Right, that's like 30-something times smaller than the sun at noon. And it would be like this. Like here's the Earth, here's the sun way over here, 100,000 miles away. From there to there. That's how you get the sun down to the horizon, using only perspective. So what would that look like on the flat Earth if we were doing it this way? Well, look like that, right? The sun would be on the horizon, but it would be 100,000 miles away, right? It would be about 3% of the size of our original sun. There's just no way that that can work. And even then, it's at 1.7 degrees. It doesn't set. It's not going below the horizon, right? It's just very, very, very small and very, very, very low, or apparently very low, but it's not below the horizon, right? We're not seeing the sun like turn it, we're not seeing this get half sized and go below the horizon from the bottom up, like what when everybody sees. We're just it's just disappearing. All right. So globe seems to make more sense with perspective, and the flat Earth. I just can't see how you can explain yourselves. Right? Your model is just not making any sense, because every day billions of people see the sunset over the flat or over the Earth. Right? We all see it, and this picture could not happen on a flat Earth. There's just no way that we would ever see that. Perspective cannot make this work. It's just not possible. So the next time you look at a sunrise, the next time you look at a sunset, please remember that perspective is not going to make it possible for you to see that. Enjoy your day. I hope you see many more sunrises and many more sunsets. Take care.